Welcome to This Explainer. Today, we're fundamentally shifting how we look at glaciers. We tend to think of them as just static blocks of frozen water sitting passively up on mountaintops, right? Well, actually, scratch that. We need to treat them as living, breathing, geological giants that actively shape our planet. I'm absolutely thrilled you're here, because this topic, it's going to completely change how you view Earth systems.
Okay, let's dive into a staggering reality right off the bat, just to understand the stakes here. An incredible 69% of all the world's freshwater is locked up in these massive icy structures. Think about that for a second. The rivers, the lakes, the groundwater we rely on for every single thing we do, that's just that tiny 31% sliver. These ice giants are literally the ultimate water towers of our planet. So understanding them is absolutely crucial to understanding our global water supply. To truly grasp the complexity of these systems, we're going to follow a quick roadmap. We'll cover the birth of an ice giant, the mechanics of motion, Earth's frozen time capsules, the accelerating global melt, and finally, the global ripple effects. Let's kick things off with Section 1, Birth of an Ice Giant. The key takeaway here is the word moving. A glacier isn't just some pile of snow that managed to stick around through the summer. To officially become a glacier, the ice actually has to flow under its own weight because of gravity. That's what makes it a dynamic, active system, rather than just a static object. It's essentially an aggregate of irregularly shaped interlocking ice crystals that actively deform and glide. And this metamorphosis from a delicate little hexagonal snowflake into solid ice, it doesn't happen overnight. It's gradually compressed over decades, or even millennia in places like Antarctica. First, it turns into granular neve, and then into a much denser layer called firn after surviving a melt season. The true magic, though, happens at that final stage when all those interconnected air passages are completely squeezed out and you get pure glacier ice. Moving on to part 2, the mechanics of motion. So if it's solid ice, how does it move? Well, glaciers move through two primary, totally distinct mechanisms. First, there's internal deformation. Because of the sheer immense pressure of its own weight, the ice actually creeps internally, kind of like a thick plastic material, with microscopic crystals sliding right past one another. The second way is basal sliding, where the whole glacier slips rapidly along a hidden watery base. You see, the glacier melts just a tiny bit at the bottom due to pressure and geothermal heat, creating this perfect liquid slip and slide over the bedrock. To really understand a glacier's health, it helps to think of it like a financial ledger. You have an accumulation zone up top where the glacier earns its income through snowfall. Down below, you have an ablation zone where it pays expenses, things like melting, sublimation, and calving. The line between them is called the equilibrium line altitude, or ELA. If that ELA rises higher up the mountain because of a warming climate, and the ablation expenses persistently exceed the accumulation income, well, the glacier essentially goes bankrupt and eventually disappears. All right, Section 3, Earth's frozen time capsules. Remember how we just talked about firn compressing into solid ice and literally squeezing out the air? Well, because those tiny air bubbles are sealed off during that final transition, scientists can drill deep into the giants of Antarctica to directly sample ancient air. It's like finding a message in a bottle from the Pleistocene. These aren't estimates or computer models. These bubbles contain the exact atmospheric composition from the day that snow fell. It creates an uninterrupted climate archive stretching back an incredible 800,000 years. And those ice cores impartially reveal a pretty stark numerical truth. By comparing that ancient trapped air to today, we can see that today's atmospheric carbon dioxide levels sit right around 420 parts per million. The ice cores prove, without a shadow of a doubt, that this is higher than at any point in the last 800,000 years. The giants have literally recorded our history for us. Which brings us to part 4, the accelerating global melt. According to the landmark 2025 GLAMB exercise, which brought together 35 international research teams, glaciers globally are now losing an average of 273 billion tons of ice every single year. Just let that number really sink in for a second. 273 billion tons annually. And what's really alarming about this data isn't just the sheer volume, it's that the rate of loss is sharply accelerating year over year. What makes this volume of loss so critical is that it triggers physical feedback loops. Basically, the actual physics of melting inherently causes even faster, self-sustaining melting. It's wild. As bright white ice melts, it exposes dark ocean or rock, which absorbs heat instead of reflecting it. We call that the ice albedo effect.
Also, as the glacier thins out, its surface drops to lower, warmer elevations, making it melt even faster. It's essentially a runaway train of physical responses.
The vast Thwaites Glacier in Antarctica perfectly exemplifies this runaway instability in the latest 2026 modeling. Thwaites actually sits on a precarious backward-sloping bed. That means as it melts and retreats inward, progressively thicker and thicker ice gets exposed to warm ocean currents. If it reaches that 180 to 200 gigaton loss rate by 2067, a single glacier will be hemorrhaging as much ice as the entire Antarctic continent does today.
Section 5. The global ripple effects. When we track these modern observations, it becomes abundantly clear that rapid glaciological changes are absolutely not some theoretical future problem. It's an ongoing, documented reality right now. Just look at 2026. Antarctica's Hectoria Glacier retreated an astonishing 8 kilometers in just 2 months. We're watching geological scale events happen on human scale timelines, monitored in real time by these incredibly precise satellite networks. And a melting giant in the Himalayas or West Antarctica isn't an isolated event either. It directly triggers a massive cascade of global consequences. We are talking about inundated coastal cities from sea level rise. We're talking about severe dry season agricultural failures and freshwater scarcity for roughly 2 billion people who rely on rivers fed by the Himalayas and the Tibetan Plateau. This whole thing reshapes global energy, agriculture, and even border security. Knowing the sheer scale of the mechanics and the melting, the ultimate question the scientific community, and really all of humanity, faces is whether we can intervene. Can they be saved? The proposed solutions out there are massive. Multi-billion-dollar geoengineering concepts are being actively tested, like building giant underwater curtains to block warm ocean currents or dropping reflective fabrics over alpine ice. But while fascinating, the definitive scientific consensus remains very clear. Rapid, sustained climate decarbonization is by far the most effective, scalable tool we have to preserve these giants. I want to leave you with this profound scientific reality: glaciers in the pipeline. Because these massive physical giants take decades or even centuries to adjust to climate shifts, a certain massive amount of future change is already permanently locked into the Earth's system. What we do today won't just define the next 10 years, it's going to define the topography of the Earth for centuries to come. With all this immense, ancient momentum locked into our planet's future, the question is, how will we adapt to the new reality of our changing ice giants? Thanks for joining me on this explainer.